In this video, I will be going through terahertz communication. Terahertz band communication is envisioned as a critical technology for 6G and beyond to meet the ever-increasing need for higher data rate communication. The Terahertz band is defined as a part of the EM spectrum and frequency band ranges from 0.1 to 10 Thertz. That is, a huge scope is available at Terahertz band compared to millimeter wave, wave band. Thus Terahertz communication alleviates the spectrum scarcity and data rate restrictions of existing wireless systems. However, the catch with Terahertz transmissions is that it incurs very high propagation losses, penetration losses, molecular absorption, etc., which substantially restrict the communication distances. Terahertz communications will be accompanied by utilizing emerging wireless technologies, for instance, reconfigurable intelligent surfaces, ultramassive multiple input multiple output (MIMO) configurations, and integrated access and backhaul at the infrastructure level, and utilizing novel signal processing techniques and networking protocols at the algorithmic level. The architecture of terahertz communication. 1. Terahertz sources. The generation of terahertz waves is a fundamental aspect of Terahertz technology. There are various methods for generating terahertz waves, including photoconductive switches. These devices use short laser pulses to create Terahertz radiation by illuminating semiconductor materials. Photoconductive antennas are commonly used for this purpose. Quantum cascade lasers. These semiconductor lasers are designed to emit Terahertz radiation and have applications in spectroscopy and imaging. Gyrotrons. These devices generate high-power Terahertz radiation using electron-cyclotron resonance. 2. Terahertz detectors. Detecting and capturing terahertz waves are equally important. There are several types of detectors. Bolometers. These thermal detectors are sensitive to terahertz radiation's ability to heat objects. They are suitable for imaging and spectroscopy applications. Schottky diode detectors. These semiconductor-based devices can be used for measuring Terahertz radiation and are often found in Terahertz receivers. Quantum well detectors. These are sensitive to specific wavelengths within the terahertz range and are used in various imaging applications. 3. Waveguides and antennas. The propagation of terahertz waves often requires specialized waveguides and antennas. These components help guide and direct the radiation, ensuring efficient transmission. 4. Modulation techniques. Modulating the terahertz signal is essential for encoding information in communication systems. Various modulation techniques are used to transmit data over terahertz waves. 6. A digital demodulator. In terahertz communication systems is a sophisticated component that plays a crucial role in extracting digital information from modulated Terahertz signals. Its properties and characteristics are tailored to ensure the efficient, reliable, and high-speed processing of data in the terahertz frequency range. 7. Digital amplitude shift keying, ASK, modulation. The terahertz frequency range involves encoding digital data by varying the amplitude of a carrier wave. Digital ASK modulation in the terahertz frequency range offers fast data transmission with good spectral efficiency. Its properties, such as binary modulation, modulation depth, and error performance, make it a valuable choice for high-speed data communication and Terahertz technology applications. 8. Voltage control. In terahertz communication, the V parameter typically refers to the voltage or voltage-controlled elements used in various components of the communication system. Voltage control plays a crucial role in controlling and optimizing different aspects of Terahertz communication. Wave to Terahertz band communication transformation. The key features associated with wave to Terahertz band communication transformation are listed below. Wider bandwidth. Wave to Terahertz band communication transformation leads to comparatively wider bandwidth, viz. Terahertz frequency band ranges from 0.1 to 10 Thertz, up to 100 GHz bandwidth available, while wave frequency band ranges from 30 to 100 GHz. Enhanced directionality, pencil beam forming. Terahertz communication exhibits higher frequency and shorter wavelength, hence smaller antenna size, than mmWave communication. Terahertz allows a comparatively large number of antenna elements to be packed within the same antenna dimension. Therefore, beams in Terahertz communication are more directional than mmWave communication. Terahertz communication reduces the transmit power and interference among the users. Furthermore, the small size of Terahertz antennas leads to miniature chip sizes. Enhanced security. In general, enhanced directionality at higher frequencies leads to a lesser chance of signal intervention than at low-frequency communications. In low-frequency communications, transmission takes place in a wide range of directions that can be received and decoded by illicit entities. Therefore, Terahertz band communications are more secure than the mmWave band communication. A comparative study of Terahertz with sub-6 GHz and millimeter wave band communication is provided in the table. Terahertz communication key benefits. The key benefits offered by Terahertz band communication are listed below. Ultra-high data rate. Due to the availability of a huge spectrum at the Terahertz band, Terahertz communication ensures an ultra-high data rate, around 100 gigabits per second, to meet the increasing need for a high data rate of 6G communication. Microsecond level latency. Enhanced energy efficiency. Backward compatibility with mmWave bands. Like microwave and IR waves, Terahertz waves are non-ionizing in nature. Furthermore, like microwave and IR waves, Terahertz waves may penetrate through non-conducting materials such as clothes, wood, paper, plastic, etc. Terahertz communication band has a lesser impact on the human body because of its non-ionizing nature. Terahertz communication spectrum. The spectrum between the mmWave and far IR bands is defined for Terahertz band communication, 0.1 to 10 Terahertz. The Terahertz band is also called no man's land, traditionally, because the Terahertz frequency range is considered too high for RF but too low for light. The Terahertz band is sometimes also called a Terahertz gap since the Terahertz band has not been technologically and commercially developed yet. The spectrum below the Terahertz band is defined for many applications, such as radio, TV, cellular systems, Wi-Fi, radar, GPS, etc. The spectrum below the Terahertz band, i.e., greater than 10 Terahertz, is defined for optical wireless communication systems. Potential applications/use cases of Terahertz communication. The potential use cases of Terahertz band communication are listed below. Extended reality, XR, and holographic teleportation. XR comprises augmented reality, mixed, and virtual reality. These services have strict requirements for high data rates and high reliability, low latency. Only Terahertz band communications can fulfill these requirements. Industry 4.0 and digital twins. Industry 4.0 is moving in the direction of almost fully autonomous missions between machines and robots, involving limited human involvement. A digital twin uses physical world data to generate models that can forecast how a product or process will work. These models can be incorporated with Industry 4.0 to improve productivity. These applications have high data rates and low latency requirements. Terahertz band communications can fulfill such requirements. Connected robotics and autonomous systems, CRAS. CRAS services typically cover self-driving, services to a group of vehicles, etc. Such services require high data rate real-time maps to exchange with vehicles. Terahertz band communications can fulfill such requirements. Non-terrestrial networks, NTNs. Due to the availability of ultra-large bandwidth at the Terahertz band can provide NTNs communication, i.e., the probability of line-of-sight links between NTNs is high, at very high data rates. Vehicular to infrastructure, V2I, Terahertz link. In a vehicular scenario, a V2I Terahertz link may be established in futuristic V2I communication to provide high data rate connectivity to vehicles at the Terahertz band. Conclusion and challenges. Terahertz band communication is undoubtedly a technology that is growing and leading us towards 6G. Terahertz band communication will alleviate the spectrum shortage and data rate restrictions of existing wireless systems. By achieving a high data rate, Terahertz band communication will cover various demanding applications: Viz, XR and holographic teleportation, Industry 4.0 and digital twins, CRAS, NTNs, V2I applications, etc. Telecom companies will have the following research challenges in the coming year. Developing a chip that can produce terahertz waves. Resource management techniques. Channel modeling. Prominent role of integrated frequency bands. Advancements in directional antenna arrays are required to overcome the challenges of penetration loss, propagation loss, molecular absorption, etc. Thank you for joining me on this journey.